Hi, and welcome to Module 14. In this module, we'll learn about Edwin Hubble's analysis of the intergalactic space of the universe.
Okay. In our attempt to understand the cosmos, we need to fathom the huge, pardon the pun, distinction between the terms interstellar space and intergalactic space. At the conclusion of Module 13, we looked at the concepts of voids in space. These are the huge regions between the galaxies. They're called the voids, or intergalactic space. In individual galaxies, the space between the stars, such as the 600 billion stars in our own galaxy, is called interstellar space. So a star 13.7 million light years away in our galaxy is an interstellar star. In Hubble's concept of the expansion of the universe, the galaxies and solar systems do not take part in the general expansion of the universe. The mutual gravitation of 600 billion stars holds them all together. The distance between the Earth and the Sun and all the other stars in the Milky Way galaxy is not expanding. What is expanding is the space in between the galaxies. The galaxies stay bound together as groups because of mutual gravitation. So in Hubble's view, what is expanding in the universe is the distance between all galaxies. It's the void space expansion.
The redshift of superclusters indicate that the universe is expanding. In the 1920s, Hubble and Humason recorded the spectra of many galaxies with the 100-inch telescope on Mount Wilson. Using the Doppler effect, Hubble calculated the speed at which each galaxy is moving away from us. Combining the additional technique of using Cepheid variables to determine galactic distances, he found a direct correlation between the distance to a galaxy and the size of its redshift. Galaxies in distant clusters and superclusters are moving away from us more rapidly than galaxies in nearby clusters and superclusters. This recessional motion pervades the universe and is called the Hubble flow.
The most amazing part of Hubble's discovery was that faraway galaxies are moving further and further faster away from us than local galaxies. And this recessional motion is called the Hubble flow.
Note that the fainter, and thus more distant a galaxy is, the greater its redshift. Recall the Doppler effect is the change in wavelength of radiation due to relative motion between the source and observer along the line of sight.
So here on the left we see 5 stars. At the top, the star is very close, and its light extends beyond the H and K line here in its spectrograph. If we look at the bottom, we see in this image that the light is not extending past the H and K line. And this tells us that the light has shifted to the red, and it's shifted much further than local galaxies.
Hubble then plotted the redshift data on a graph of distance versus speed, and he found that the points lie nearly in a straight line. The linear relationship between distances to galaxies and their recessional velocities is known as the Hubble law. The Hubble law describes our expanding universe.
And here we see it, the Hubble constant, it's called. Notice that when we plot velocity versus distance, we get a plot that's nearly a straight line, and therefore there is a definite relationship between velocity and galactic distance.
So the formula for Hubble's law is V equals h subscript 0 multiplied by d, where V is the recessional velocity, d is the distance, and h subscript 0 is the Hubble constant. It is the formula for a straight line, and the Hubble constant is the slope of that line.
Again, these are actual plots of galaxies. If there was no relationship between velocity and distance, the plot of galaxies would not fall on a straight line. This is what we call the algebraic truth.
The relationship between the distances to galaxies and their redshift was one of the most important astronomical discoveries of the 20th century. It tells us we are living in an expanding universe, and the Hubble law reveals the speed of that expansion.
So, using the Hubble law formula, look at these two examples. A nearby galaxy at 6.25 million light years is moving at 88 miles a second, whereas 100 million parsecs away is moving at over 600 million miles an hour. Crazy, crazy, crazy talk. Welcome to astronomy. We have another modern conundrum in astronomy, something called dark matter. The mass of a body determines how much gravitational force it has. However, in recent years, astronomers have added up all the mass of stars and galaxies, and they seem to be missing a certain amount of mass, namely by tenfold. And so instead of thinking that we don't understand properly gravity yet, we've hypothesized an invisible kind of matter called dark matter. Again, if it acts like gravity, smells like gravity, and talks like gravity, it's probably some form of gravity, not an invisible form of matter that we can't see or detect. So in this module, we learned about the Hubble flow, the Hubble law, the Hubble constant, and the concept of dark matter.